Hello, my name is Andrew Lamb. I'm going to now present a talk that I gave a couple weeks ago at Tokyo Conf in Portland, which I thought was interesting. I think that talk will be there online as well that I actually gave there, but this is probably a better uh, venue. And hopefully I'll provide a little more background and context that I wasn't able to go into in the time that I had on the actual stage. So this talk is titled basically how we use Tokyo for CPU-bound tasks, and it works really well. You might imagine, of course, that if I start off the talk with a question about whether or not you should use Tokio for CPU-bound work, right? Tokio is a Rust library, typically designed for networking. Obviously, my answer is yes. And of course, we've been doing this for 5 years in Data Fusion and at FluxDB and elsewhere. Uh, I actually wrote a blog post approximately 4 or 5 years ago that had the same thing. So I rage wrote a blog post because people kept telling me that Tokyo is a bad choice for CPU on work. I think it's a great choice. This is my talk and pitch as to why. I made it once in this blog post, and then this is sort of like the talk version of it that hopefully is interesting to you. So anyway, let's move on. My name is Andrew Lamb. I'm a staff engineer in Data. I spend a lot of my time working on upstream projects that underlay our query engine, specifically for Apache Data Fusion, Apache Arrow, Apache Parquet. I'm mostly going to talk about Data Fusion today. I have also worked quite a lot on databases and compilers over my career, and I am somewhat ashamed to admit that I've actually implemented my own allocator and threads task scheduler at least two companies in the past. So I'm pretty well versed as to why it's a bad idea, and all the more reason why I think Tokio is a great idea. So let's move on. In order to explain why Tokio is a good idea, I need to explain to you the actual use case we're using it for, and that is a database execution engine. So in order to understand that a little bit more, I'm going to do a crash course and give you what I think you need to understand. So at a high level, what a database execution engine is a data flow graph. So what that means is like data flows through a graph. So nodes and edges, right? Nodes represent processing, edges represent the data flow between them. We'll review that briefly in a little bit. Here's a canonical example SQL query, right? Many database engines use SQL. And so they have this relational operator notion. And so this query basically selects from a table called hits. If you're familiar with ClickBench, you'll know this. It has a predicate that looks for only URLs that have Google substring. It then groups the user ID and it gives a count. Right? So it's basically a select filter grouping. And the way this is represented in a typical execution engine is that as a data flow graph. So at the bottom would be a file reader, represents the from clause, then a filter, which represents the where clause, applies the predicates, filters out rows that don't match, then some sort of grouping or aggregate operator. It's called group by hash in data fusion, but it can be called many other things. But it all basically, this is what does the grouping. And so that's basically what most query engines will give you. That'll give you some version of a plan like this. There's lots more details that you can go into about query engines. I have a whole talk about how data fusion works in general, but I think that's a high enough level idea to get where we're even use Tokio. So as I mentioned, these things are data flow graphs, right? This is the plan. I've got my red, green, blue nodes, and actually what will happen is the data flows from the bottom to the top. And so in this case, the data is my little pink block, right? It would then flow into filter, and then the filter would output the results of the rows that matched, and then you'd do grouping, and eventually when grouping is done, it would produce output. So you can feel like that data is flowing from the root, or rather from the leaves of the tree up to the root, and it's shown top down for whatever reason. But that's the typical way execution plans are shown. Data Fusion does it the same way. And basically, these things are data flow graphs, right? So so where do we need a scheduler? Well, you need a scheduler to basically figure out when you're running CPU, what data the CPU is going to be pushing at any particular time. And for databases in particular, it's very, very important that the data that is basically data that's created and then consumed, specifically filtering and aggregates are the classic example, but joins or other has this property as well. As soon as the data gets produced, you basically want to process it on the same core. You want to keep the same core processing the data as it flows up through this graph. And that makes a lot of sense, right? Because this will generate data and often it'll immediately get filtered. So you don't want to spend a lot of time sending the data that you just created into, put it into the CPU's cache to send it to main memory just to bring it back to throw most of it away. Like you want to keep it all in the cache as much as you can. So that's like basically one of the most critical requirements for a execution engine scheduler. And I'll explain how Tokio does that. Great job. I'm not going to describe vectorized query engines in any depth in this talk. I'm going to spend most of the time talking about Tokio. If you want to read more about data fusion or databases in general, you can come join the Data Fusion community. We have lots of people doing this stuff. You can learn all about it. There's also a bunch of papers and references on the slide, and the slides will be available. So I just want to point out that's where my database specific stuff is going to end here, I think. And now I'm going to switch to Tokio and talk about moving stuff through the plans. So the question, of course, becomes how do we move this data through the plan? And I showed the initial very simple plan of just data flowing through one of those filter, a reader filter group by. Data Fusion actually implements a classic and very fast mechanism called like I guess a classic, you'd call it a volcano style scheduler, but basically each one of these things runs in a single, wants to run on a single core, and then there's certain parts of the plan, Data Fusion, they're called repartition, and the classic database execution engines, they'd be called exchange operators. So Data Fusion implements those, and those are places where the data crosses a thread boundary. I, I'm not going to talk about that in any detail, but I'm just going to talk about how you focus scheduling down here. And again, basically the scheduler's problem is you want to map these CPUs to the data that's flowing through these sub pipelines. In this case, we have one pipeline per core, and then we want the cores just like ripping through this stuff as fast as possible. And the thread scheduler is supposed to be matching that. All right. So that I think I've talked quite a bit about the requirements, and I've sort of pre-hinted at this. Very important, as I've mentioned, probably over-mentioned, that as soon as you produce the work, you should also consume it as much as you can. Obviously, want to use all cores, and these days in the modern day, you have like 20. I have 20 cores in my aging laptop. I personally think it's very important that it's easy to understand or program. I think systems programming maybe is not the easiest thing ever. Maybe it won't matter now that all the AIs are in the code, but in general, I think understandable abstractions is really important. And I also believe it's very important that it's like well-tested, battle quality code. I have spent a lot of my life, professional life, chasing down weird race conditions in custom written thread schedulers, many of my own making. So I would prefer not to do that again. So like I don't want to be chasing down someone else's weird thread schedule. I also think it's very important that came up in our evaluation is that you also need to have a story for however you're scheduling these threads, right? Like at some point, databases almost always have to do I/O to a remote system, either like a local SSD or they have to go out to object store. It's very common these days in disaggregated database systems. So in other words, whatever you're doing for thread scheduling, you have to make sure that you're ready to like actually wait for network and I/O in general, and as caching layers and blah. So basically, you can't think it's important to have that as a first class citizen, not just sort of bolt it on after the fact and be like, oh, not everything actually runs on local files. Like, no, not everything runs on local files these days. All right. And by the way, even if they do run on local files, the properties of what those local files and file systems look like are changing with these crazy SSDs. If you read some of the modern papers about IOU ring and what you need to do to really take advantage of that. So anyway, without going too much into detail, I think what this means is that the Tokio ecosystem sounds like a great plan. This is my assessment, right? Like you already have it because it's basically the de facto scheduler for IO in Rust. So you don't need a new dependency or a new dependency chain. It's a lot of effort's been put into a very sophisticated, hand-tuned work stealing scheduler. From my perspective, it effectively has built-in language support. So that means the Rust compiler will generate futures and streams for you using async and await. Some people like that, some people don't. But compared to writing that stuff by hand, the Rust compiler is a godsend, in my opinion. And then there's already a whole bunch of streams and libraries and docs about how to do asynchronous locking and channels and how to deal with cancel. Also a fun place that I've spent a lot of time chasing debugs. I think the people at Tokio did a great job making it heavily tested, and that's part of why it's used heavily across the Rust ecosystem. And I didn't just say that because I got invited to talk about Tokyo Conf. I actually believe it. It has great properties for cache locality, which I'll explain in a second. But basically, it means that if you're doing something and you create a future and then you await on it, like the thread that calls await is going to run that future if it's ready. Which is a very important property, which we'll talk about. And of course, it's well documented, actively maintained. I was at a conference where they're talking about Tokyo. So it was great. So I thought it was a great idea. Let's do it, right? Wrong was basic, so everyone I first suggested this idea to said it was a terrible idea. The first thing they immediately cited was the Tokyo docs, which as of 1.10.0 told me basically most people interpret this as do not use Tokyo for CPU bound work. In particular, it said if your code is CPU bound and you wish to limit the number of threads used to run it, you should run it on another thread pool such as Rayon. Blah blah blah. Something about channels. I can't tell you how many people cited that one sentence to me and said that means the Tokyo authors themselves they don't use this for CPU bound work, so therefore you shouldn't do it. It's not actually what they meant. That what they actually meant is you shouldn't use the same runtime instance, aka the same thread pool, right? Like if you can actually have two runtime instances, two different Tokyo thread pools. So it's not about the Tokyo software necessarily. It's about the fact that you don't want the same threads competing for I/O and CPU work, which I'll come back to later in this talk. So thank you know. So how do we fix that? Well, I went and thank you to Alice. We got a additional sentence in there that basically said it's okay, if you want to, if you really know what you're doing, you can use Tokyo runtime for CPU run tasks. And also to these people credit, early versions of Tokyo, it wasn't as clear that you could use second runtimes. Like now it's very clear the docs are well documented, but early on it was not clear that that was a thing that was even possible. Yes, and we also added the caveat again, you've got to be really careful not to use the same runtime. Yeah, and so again, thank you so much, Alice. I probably never interacted with you after this, but and this PR probably had the greatest um, ratio of like comment. It was like a two-page justification as to why we should make this change, and then like it ended up being two sentences. So, but anyway, thank you, thank you, thank you. This made my life so much better, and I think it helped Tokyo a lot. So another argument that I would often hear is that tail latencies are really bad. So what is a tail latency? Tail latency, like if you look at a general idealized system that's doing network requests or really or any request processing, in theory, you would like sort of every request you would expect as long as the system doesn't run out of resources, that it's not resource bound, that every request is going to take the same amount of time to process. It turns out in real life there's a tail, so some number of the requests take longer for some reason, like maybe your computer decided that was a good time to do apt-get update, or you refreshed on your browser, whatever it is, right? Like there's some number of requests that take longer, even in general. If you're not careful for reasons we'll talk about a little bit later, uh, you don't want that tail to be big, right? You don't want some requests to take huge amounts of time, especially if these are network requests, because that is in the range of things like where the network stack starts throttling you because it rightly assumes that you're congested, aka you're not able to respond to packets fast enough. And it's also like, in extreme cases, the zone where you end up getting killed by things like Kubernetes or other orchestrators, which basically say, hey, process you alive. And if you don't get around to responding in time, they decide that you're not and they just restart you. So people would say that using CPU bound tasks increases these tail latencies is unacceptable. This is basically another version of you shouldn't use the same runtime on for IO and CPU bound work. This comes up a lot. So basically, must use a different thread pool. Another thing I heard people talk about was how uh, Tokyo has high per task overhead, which is true depending on how you look at it. At least it's true compared to like toy examples. Here's an example, which is a terrible idea, probably used for Tokyo to like do queue sort on individual rows, right? Sort each individual row of the task. Unsurprisingly, that's a terrible idea, and it goes really slow in Tokyo. But it's so silly. And also, you know, like I said, I've written my own thread pools. It's very easy to make ones that go faster on toy examples. It's very hard to make a production grade one that works real. So I like Tokyo. So, and again, let's talk about what high per task overhead are, right? So let's talk about how big the tasks are. So if each little task does a small amount of work, I purposely made this uh, diagram smushed, right? Like if you got a certain amount of overhead and you're only processing a single row at a time, yeah, the overhead of a Tokyo task is pretty high, right? It's got a function call, probably an allocation in there, not sometimes not great. However, if you process 8,192 rows, which is the default, by the way, batch size with Data Fusion, and that's just one array. It's actually typically multiple columns of this. The amount of work done compared to the scheduling overhead, it basically is impossible to measure. And I've looked at it, you never see the Tokyo scheduler overhead in Data Fusion plans. So as long as you make your task sizes large enough, it's totally fine to use Tokyo, and it works great. Oh yeah, by the way, this is called for some reason the database we call this vectorizing. Vectors, these collections of rows are called vectors, but it's basically a classic amortization story. The other thing I heard quite a lot is that Rayon was for CPU bound tasks, right? So instead of using Tokio, you should use this thing called Rayon. Rayon is a great library. It has a bunch of parallel iterator mutation. By the way, I wasn't just saying this. Nico Matsakis was presenting after me at Tokyo Conf, so I didn't want this to come across as just trying to flatter him. No, it actually is great. Sometimes we've used this wonderful. And in fact, we even had Raphael try it. Tussfold is his username. He was one of the ones who I think really didn't like that Tokyo was used for CPU bound work and had a lot of because there are places where it's a little rough, and so he really wanted to make something that worked better. And so he actually tried scheduler using Rayon, and it turns out he couldn't make it faster. It was challenging to basically bolt on async IO, especially when you had to do back pressure, right? Like you don't want to produce data out of a scan faster than you can consume it upstream, or especially when your plan's broken into multiple stages. So it was quite a lot hard, and eventually we moved this code because um, it wasn't any benefit, and it was a lot of code, so we deleted it. And so again, I don't want mean to say that he did a bad job. If anyone could have done it, Raphael could. But I think this, in my mind, was great evidence that Tokyo is ready and up for the job. All right. So what do we actually do? I hope maybe I've convinced you, maybe not. Regardless, I'm going to tell you how Data Fusion actually uses Tokyo for the scheduling. So the way it does it represents the data flow graphs that I talked about earlier in the database execution engine as Rust async stream. So like literally the stream trait. And in this case, sort of the mental model is you get a record batch in. So that's sort of like a bunch of columns in. Then there's a bunch of nodes that implement a trait called sendable record batch stream. So they're like arc, dyn, whatever. Uh, and what they are is they're basically dynamic streams that, as you call pull next on them, they produce record batches, well, result of record batch. And so basically, this now is the model for the execution graph that I showed earlier. Right, the execution engine has this data flow graph. The graph nodes are like stream instances, and the edges they are connected. Each implementation of a stream typically has one or more inputs, also streams. So with that, you can build up the operator tree, like or the execution plan, the data flow graph, like I described. They're often called operator trees too, but data flow graph is my preferred mechanism or preferred nomenclature. All right, so here's an example, right? This is basically the simplest node you can come up with. This is the initial implementation of filter. By the way, you can implement this. This is a manual implementation of filter. You could or of stream. You could also use like just a classic. You could use one of the combinators in futures, the futures crate. Make this like one line long. I'm using the multiple ones because this is how it's actually implemented. But again, it's you can use the existing Rust ecosystem to write these things in much less code. So in this case, I'll just walk through it. It says we have generating result record batches. When you need the next record batch, it calls pull next, right? Because it's a stream. That's the contract of a Rust stream. The first thing it does is it checks whether the stream is done and returns like none. This is the contract of a stream that's already completed. If that's not true, then it actually asks the input, right? Basically gets the next batch from the input. And it'll also, if the input's not ready, that gets returned. That's this magic ready macro. If the input was done, we mark ourselves as done and return none. If the input actually had work to do, oops, I didn't point out. If the input actually had work to do, here, this is the actual work, right? So here's the CPU bound work, predicate, evaluate, filter, record batch. This can be very CPU heavy to actually compute this. And then you return the result. So, this is implementing a very simple state machine. It like gets the input for the next batch, applies some CPU, returns. And then, by the way, this last one's return error. Uh, but I think this is about as simple as you can imagine a filter being without hiding all the details, right? This basically shows all the quirk. It's I really like how this is implemented. It's not quite the real filter right now is not quite as simple. The biggest difference. This is actually, this is what the current one does. Like this is more close to what's on Data Fusion main. The major difference, you can still see it's basically the same structure, but in this case, there's like a mini buffer inside filter exec, so there's not a one-to-one mapping between like one batch comes in, one batch goes out. It actually might fetch multiple inputs before it produces an output. And it uses this thing called a batch coalescer to do that. And that's just to make sure that the amortization that we were talking about earlier actually happens, especially for very selective filters. Like if you only pass one or two rows out, you really don't want to be passing record batches that have one or two rows. It waits to build up enough rows before it passes out. But otherwise, it's basically the same. And so this also shows an example where you don't have to have a one-to-one input correspondence with one input, one output. You can read multiple input batches in before you produce output. And it's in a loop, so it doesn't actually necessarily return. If as long as the input's ready, it'll just suck input in the context of this loop. So there you go. I mean, this to me is, I personally think this is beautiful. I'm obviously very biased, but I think this is very clear and easy to understand. All right. And so now I want to get back to talking about this like Tokio core mapping thing. This is one of my own personal annoyances that people will often cite. There's this seminal paper called Morsel-Driven Parallelism out of the TU Munich database group, and I'm paraphrasing here, but it basically says in order to keep your work connected to a CPU, you really need to use a push scheduler with morsels. Is at least how people interpret the paper a lot of times. And I think it's incorrect, frankly, that interpretation. And I wanted to show an example of how this Tokio model, actually what Tokio does, and then how it keeps the work on the same core that, like when the data gets produced, it also gets consumed by the same core. So in this case, imagine we're going to walk through that call chain of pull next. So here you got the repartition, right? So starting here, basically you want the output. So you call, give me the next output. That turns around, which calls pull next. Then that turns around, calls pull next on its input, just like we saw in the filter. Then that calls on its input. In this case, it's the filter stream pull next. This is what we just looked at. Then that will call pull next on the file reader or whatever this is, right? The data source stream. In this case, it's the file reader. This has no input, so we'll presume somehow it makes data internally and it returns the batch. So it literally returns the batch. If you look at the call stack on profiles, you'll actually see these methods, and there's a bunch of Tokio stuff between them, but you'll basically see this call stack. And why that's important is because it literally means from like a normal programming perspective, it's as though you made a sequence of function calls, the inner function return the data, and now you're basically passing it back to the outer function, which is now doing the work. Right. But it has a nice benefit that if you weren't ready, you can actually return all the way up the stack and Tokio will effectively resume you down here. But you don't have to worry about that. Instead, from your perspective, you just wrote code and it basically returns the batch, right? So it returns up the stack, you return to your caller, and then it processes it. So the point is, in the case when data was ready, you literally, the same thread runs down, generates data in the file stream reader, then it gets filtered, then it gets grouped, and then it might get repartitioned, all the same core. So it never leaves cache, super fast. All right, so that's phase one, right? That's how you map execution engine data flow graphs to Tokio stream or Rust street async streams, which then get run by Tokio. And now I will talk briefly about using a separate thread pool. This is how you do it. In case that's interesting, like I talked about, you have to have two separate thread pools. You have to be careful not to try to do I/O on the same thread pool as doing CPU work. Here's an example of how you do it. You make a CPU runtime, right? That's basically the name for a thread pool in Tokio. You then make a channel where you're going to send results back to the like by default you get sort of a default runtime. So like you get there's a special macro you can add to main that effectively makes a runtime for you, but you can make another one for yourself. In this case, I'll make a new channel and I'm going to send work to be done over there. In particular, one that's going to actually do, here's the work to do SQL planning and execute stream is the actual execution we just walked through. And you get a stream back, and then by calling this stream.next, that's what's driving the plan, like I just walked through. And then this sends the results back over the channel to the original runtime, in this case, the IO runtime. And you run it on your own CPU runtime, you're done. All right, so done, no problem, right? Well, as I'm hinting here already on the notes, you can actually potentially talk like, hey, Andrew, when you're running SQL queries, like you might, or planning SQL queries specifically, you might actually have to go fetch data remotely or fetch a catalog remotely. Basically, you might have to do network IO as part of this. So you're blindly just like, oh, you can run SQL without doing IO. Well, that's, sort of the premise of the original talk was like, no, you can't. You have to do both IO and CPU to run database queries, which is true. So what actually happens? Well, in this case, you effectively provide a callback to the CPU bound tasks to call back to the IO runtime is effectively what's happened. the way it looks in this case is we use this object store crate as an object store API. And in this case, there's a way to basically set up the object store connections so that they spawn requests on the other IO handle and return them back. So this basically means when an IO happens as part of the IO request happens as part of planning, for example, it doesn't actually run on that runtime. It'll pass it back to another runtime, and then you register that with Data Fusion. So there's a whole example that shows how to do this in thread pools and Data Fusion, but it's not entirely hard. Although to be honest, the APIs for this are much better now. They used to be pretty messy, but they're quite straightforward now. Yeah, I think I just said that. All right. So the last little bit of this talk is I basically want to talk about how well it works. So DuckDB, I love ClickBench. I love DuckDB, but I also am definitely envious of DuckDB's technology and their ability to invest in it. I've just got a big open source project. They've got more resources. Let's put it that way. Anyway, so as of June 2025, we were basically 2x away from DuckDB. As of February, we're 1.6. As of April, we're 1.4. The point of this is not to say that we're great. We are, of course, but the point is over time, the performance is basically uh, converging with DuckDB. DuckDB is basically like the best that classic database people can do. It's implemented C++. It uses this morsel-driven parallelism thing, right? It's basically got all the bells and whistles. And so if Data Fusion can get close, and we will be at the same speed as DuckDB very shortly, there's no reason why that the scheduling has anything to do. Like the Tokio scheduler is doing great, and I think our performance numbers show that. Another thing, if you want a little more academic treatment, you go read our Sigma paper. This is one of my favorite charts of the paper. I'm not going to walk you through the whole thing, obviously. Basically, these are individual ClickBench queries, and the x-axis is number of cores, and the y-axis is query time. So basically, lower on the y-axis is faster, greater on the x-axis is more cores. Sometimes Data Fusion is faster, sometimes DuckDB is faster, but the point of these charts is basically the shape is the same. Right? So these shapes are showing how the query performance changes as you add number of cores. In an ideal case, you would hope it always goes down to the right. However, in a bunch of cases, at some point, the amount of work done per core is so small compared to the amount of effort required to synchronize between them, it goes back up. But the point of the fact that I think the shapes are basically the same across these systems, one using this fancy push-based scheduler, one using Tokio and a classic pull-based model, suggests to me there's really nothing about the two differences that affect their scalability across numbers of cores. Okay, so real world experience. Oh yeah, I should mention like the highest, it's kind of messy, you can't see it here, but I believe it's 192 cores is the max. So it's not just like 64 cores. The reason this gets slow is because there's really not enough work to keep 192 cores busy for that. Anyway, so that was great. Obviously, Tokio is awesome. We didn't have ever had any problems with it, right? Well, probably not. Actually, I'll just walk you through basically the two major real world things we hit. And the first, I might have foreshadowed before, but one of the things we saw in one of our early systems is sort of as you cranked up the number of threads that were driving the system, basically the number of each of these threads is running a whole bunch of concurrent queries. You would basically expect that the throughput per core, right? So this is normalized by how many cores you have. You'd expect that throughput is basically the same, like it remains constant until you hit resource saturation, and it would well, ideally it would stay the same the whole era. So basically, you're expecting a flat line, but instead we saw it actually drop off in some cases very dramatically with higher thread count. So basically, as we increase parallelism, this thing would slow down. We're trying to figure out why. By the way, resources weren't saturated, so the CPU wasn't maxed out, network wasn't maxed out, memory wasn't maxed out. So what was happening? You can probably guess. So then we actually had this great picture. I think Raphael made this or Marco made this. One of them. It's great. It actually shows you all the different the two different thread. We had two different thread pools. Everything was great, but it turned out at these higher concurrency levels, the I/O for some reason all the I/Os just took longer. Right? We never couldn't really like everything seemed like it was okay, but just for some reason the actual syscall took longer. And eventually we tracked it down to, despite knowing better, we were actually intermixing IO and CPU tasks in the same thread pool. So in particular, what was happening is didn't have some of those callbacks set up to do IO from work initiated on the CPU pool, and so therefore, basically, from the network stack's perspective, we weren't processing tasks fast enough. Like the CPU bound task was cranking along with CPU work, and often it wouldn't respond to network events quick enough. And so the network stack reasonably interpreted that as if the host was congested, and so stopped sending traffic to it as fast. Basically, lowered the priority of its traffic inside. So that was bad. However, once we moved the IO thing off in a PR that we've has the epic name of Bodge. I can't remember the Bodge PR. We referred to it for a long time because that's Raphael thought it was a hack basically. Once we merged that thing in there, it worked great, which is because we stopped doing IO on the CPU. All right. So again, very important to have two separate thread pools, as we talked. The other thing that I don't think I'm going to be able to do justice. This is the best picture I had for it, but it comes out of a great blog post by Pepin. You can read all about that. Basically, because we're using Tokyo's model, right? And as I showed earlier, if the data is ready, it'll just immediately just like sit there and churn. It turned out it's really good at that, and sometimes it never returns back to the scheduler. And so, in particular, that means sometimes you can't cancel the. There are certain cases where you couldn't cancel the queries because from Tokyo's perspective, they could always make progress. And typically, the queries you couldn't cancel were stupid ones that like people didn't really want to finish anyway. Like they did some giant cross join or whatever, which was a mistake. And then they were trying to cancel it so they could fix their query. But because Data Fusion just happy to sit there and churn through and just generate lots of data, like throwing most of it away immediately, uh, without ever returning to Tokyo, so that Tokyo could like cancel everything and shut down, that was a pain. By the way, I've had versions of the same problem in other database systems, and it's always like basically the solution is you have to come up for air every now and again. And Pepin did a great job of like there's a lot of subtlety in that and how to make it work and work within the context of Tokyo. And this blog, I would definitely recommend reading it if you want to know all about that. So anyway, thank you very much. I enjoyed this talk a lot. Having the chance to give it. Thank you very much to Mustafa Aker, who suggested in the first place that I submit the talk to Tokyo. Thank you to the Tokyo people, Tokyo Conf people, for Carl and Alice specifically for organizing and having me here. And because part of my job is basically begging people to come help us, right? Like, please come help with Data Fusion Arrow. I don't have uh, an army of people that I can control. I have just whatever influence I can gain by making YouTube videos and various other things. So, basically together we make this great thing. We'd love to have you. So anyway, thank you very much. I hope you enjoyed this, and I will see you online.